light in the universe, and we can see it. And why is it there? What is it? Well, before that time, the universe was very hot and very dense, and it was in the form of plasma. So there are no stars and galaxies. There aren't even atoms, because it's too hot for atoms to form. So there are electrons floating around and atomic nuclei, mainly hydrogen and helium, that were made closer to the Big Bang. In that state, the universe is opaque. So light can't travel through it. So you can't see through it, essentially. But at that moment, as the universe is cooling down, the atoms can form. So it becomes cold enough for electrons to go into orbit around the atomic nuclei. And at that moment, and it almost is a moment, the universe becomes transparent. And that light can travel across the universe. And we have telescopes or satellites today, like this one called WMAP, which can look back and capture that light and take a photograph of it. Now, the best satellite we have at the moment is a European one called Planck, and it took this photograph. So this is a photograph of the whole sky, so that's why it's a sphere. There's every direction around the Earth. So this is as far away as you can look. It's 13.8 billion light years away, essentially, 13.8 billion years back in time to a moment 380,000 years after the Big Bang, when the universe became transparent, the oldest light in the universe. Now, when this photograph was first taken, I should say that it's often called the afterglow of the Big Bang. It's called the cosmic microwave background radiation. When it was first discovered in the 1960s, it was the crucial bit of evidence that convinced everyone, pretty much, that there was a Big Bang. Because what you're seeing here, you're seeing a universe that's different to ours today. It tells you the universe hasn't been in existence forever, filled with stars and galaxies. If you look at this, it is a formless, featureless universe with no stars and no galaxies, just glowing hot. Not quite featureless though. What you're looking at here is different colours which correspond to areas of very slightly different density in the young universe. It's smooth to 1 part in 100,000, but there are these little areas that are slightly denser than the other ones. Now, when George Smoot, the physicist who got the Nobel Prize for seeing these little differences in colour in that light, when he gave his Nobel speech, he said that this image is like looking at the face of God. And George Smoot is not a religious man, but what he meant was that these are, in a very real sense, the seeds of our creation. Because these tiny little overdense regions in this young universe ultimately seeded the formation of the first stars and galaxies. So without them, we wouldn't exist. So they're vitally important for us. But the question then arises, how did they get there? Why is this universe almost smooth, but not quite? What is this telling us, this distinctive pattern about events that happened before this time, closer to the Big Bang? Well, I'm going to describe to you the best theory that we have. Now, this is a theory that was first proposed in the 1980s, and it really came to maturity, I would say, in the last 10 or 15 years. So it's not on the same standing as Einstein's theory of general relativity. It's not been tested to the same extent, but it is the best theory that we have to explain that structure in the universe. It's called inflation. It's always been on here, actually. It says that inflation and quantum fluctuations in this kind of hazy mess of the Big Bang. What's happening there? Well, the theory starts with a little patch of space. And I'm going to show you a simulation using the physics that we know about how that little patch of space evolves into the universe we see today. So this little patch here is 1/1000th of the size of the nucleus of an atom. So it's a very small little patch of space existing in the universe.